Okay, so you should be seeing my first slide. And I'm going to start then with my talk from zero to deep learning. Just one little word before I start. This talk really is about from zero to deep learning. So a lot of the talk is about understanding what deep learning is and its founding principles. So there's we're only gonna see code at the end of the presentation, and not a lot of it. So if you are already a deep learning expert, probably you're gonna hear a lot of concepts that you're already familiar with, just as a word of caution. Who I am has already been explained very nicely by Mary. I work in Amsterdam. I live here too, and indeed, I am a community manager here. I run the Reactive Amsterdam meetup, and I'm also the organizer of the Kubernetes Community Days conference. Last year it was a big success, but this year, in fact, with this entire, lockdown and COVID situation, we've just decided to postpone it to directly to 2021. It was a painful decision, but we believe it made sense. So yeah, I hope that 2020 doesn't repeat itself ever again. All right, now to get into this talk. Before I actually get into deep learning, I want to share it with you the idea that brought me to it, the planes idea. We're going a little bit back in time here. About a year and a half ago, I was working for a client whose office was next to the Amsterdam airport, Schiphol. And what you see on screen is a portion of Google Maps screenshot around the airport area. And if you look at the history of the airport, this section that you see now highlighted, that first sort of airstrip, was the one that was built first. And in time, the traffic increased, everybody started flying before 2020, obviously. But so let's say after the Second World War, at some point, there was a necessity for another strip to cater for more airplane traffic. And so a second strip was built, which is the one that you see now on the screen. Now, as you can see, though, in between these two areas of the airport, there was already that yellow highway in the middle called A4. Well, the solution that they came up with in order to let these two areas communicate is actually build a bridge over the existing highway. And so the result is, and I'm sure if you've ever been to Amsterdam, you've probably noticed by landing or taking off, that the airplanes, they go just on top of the cars passing below them. And I happen to work right next to it. So the view from my office was something like this, where every now and then you would see these huge planes strolling peacefully meters above, these tiny cars and people passing just below them. And I know maybe from the picture it's not really impressive, but when you see it live and moving, it was really incredible. One of the problems is, of course, everybody in the office wanted to take pictures of this plane because it's so amazing, but you don't know exactly when they are going to pass. And so you don't know exactly. You should keep an eye on the window all the time. So that is where my idea came from. I am going to put a Raspberry Pi on the window with a camera that takes continuous pictures and movies of the bridge, and I'm going to train a neural network to tell me whether there is a plane on the bridge or not. And if there is one, I am going to tweet about it. And note that I knew almost nothing about neural networks before this project, so it was really just a way for me, a playful project to learn something new. This is the setup that I created, my little Raspberry Pi at the window. You can see there is a bridge at the end of the road with actually a plane, a white plane on it. And the pictures that this Raspberry Pi would take, they are on the on the right column of the slide. So on top, there's a picture with a plane on the bridge, and then there's a picture without the plane on the bridge. And then when I set it all up, the result is that this Raspberry Pi was automatically tweeting at this Twitter account, Planes on Bridge, some pictures with some planes on the bridge and some random quotes. And I have to say, with 17 followers, it probably wasn't the most popular Twitter account ever. Also, it's mostly my friends and family, those followers, but it was a lot of fun running it. Now I have this broad introduction to the idea. Let's go a little bit into what deep learning is. So deep learning is an actual subset of machine learning, which is an actual subset of a broader concept of artificial intelligence. And deep learning is a bit of a synonym of neural networks that you have heard as well, all these neurons connected to each other. And the two common use cases for machine learning or deep learning are regression and classification, where regression use case basically tries to answer a question that is how much. In the graph you see there, that graph might be, a series of measurements that you have done. Could be any field. Let's say, I don't know, the house price given its square meters or square feet, I think. And so your network, given one of these input, will try to predict the other one. Given square feet of the house, will predict its selling price and things like that. Whereas classification answers the question, what kind? So usually you have a few classes of different objects, item, and you want to sort of tell one from the other. In that picture you see on the screen, it's that famous experiment that someone tried to build a neural network to tell chihuahuas from blueberry muffins. And as you can see, even for a human, it's not always that obvious. And so, training a network that can see these differences is quite a task. And if you go to our case, then of the planes, it's indeed a classification use case, and the classes are simply two. We want to know whether there is a plane on a bridge or no plane. Before we look at how I built it and how we can build it on the JVM, let's look very quickly about the basics to the basics of neural networks. The very fundamental unit is the artificial neuron. And this artificial neuron is composed by different parts, but the core one is simply a mathematical function called transfer function. This transfer function is a function that takes several weight inputs, in this case W1, W2, and so on. The transfer function computes its result given these inputs, and there will be one outcome, and this outcome is put through another function called activation function. Now, in practice, this activation function is just a filter. So something that decides whether the global output of this neuron is going to be the result from the transfer function or zero. So in a sense, the activation function can sort of mute the transfer function. And this is basically it. It's just some math, but not even a lot, two functions one after another. And then once you've seen this, you might be wondering, well, wait a second, this doesn't look very powerful, does it? There's nothing really special about it. And you wouldn't be wrong. In fact, the artificial neuron is not very complicated, but their extreme power, though, comes when these neurons are combined in many different configurations. They generate what is called a multi-layer neural network. And so typically it looks like this. If you read it from left to right, you see that those inputs, there's some input values to our network. It will be first injected into an input layer, which are some neurons that typically they just take the input and just propagate the information through. And what you can see is that each of the neurons in the input layer each one of them propagates its information to the neurons of the first hidden layer, and so on. So each neuron in the hidden layer will apply its transfer function, pass it through its own filter, and so maybe some of those neurons will propagate the result to the second hidden layer, and so forth. And all the way at the end, there is an output layer which is tasked with the task of collapsing the information that comes from the previous layers and basically emit some output values. So as you can see, as the number of neurons per hidden layer grow, and as you have more and more layers, the combinations are practically infinite. And this is also why neural networks require an incredible amount of power to work. And in fact, only in the last decade or so, we were able to put all this power together sort of easily. One example, the way this would work, just to visualize it, let's say our input values on the left are A, B, and C. Our input layer neurons will just take those input and propagate it to all the neurons from the first hidden layer, and then some of the neurons in the hidden layer will propagate their results to the neurons in the second hidden layer, and again, some of them will propagate it through to the output layer, and the output values in this example will be 2 and 5, for instance. Now, what happens if I change the inputs on the left? So now we have T, P, and G. The input layer is just going to propagate it all as usual, but what happens next might be an entirely different configuration, and the output values will be 7 and 1. Now, this example lets me show you briefly why these networks are called deep network. Those layers in the middle are called hidden layer because we, as humans, after that the network has been trained, the combinations are so many that for us it's really difficult to see what happens in the hidden layer. Remember that each neuron has some weights on the inputs, so those weights will change from neuron to neuron. And how this entire network of neurons will work, it's practically impossible for us to predict or to go and see in details. And this is why that's where this name deep comes from. It evokes sort of deep ocean or something, some obscure area difficult to explore, and that's exactly what happens in the hidden layers. Now, we have established what these neural networks are. Now, what happens is that in practice, if you implement them, there are going to be different types of neural network or deep network. And if we want to give a look at some of them, probably the most important in everyday usage nowadays is convolutional neural networks. Convolutional neural networks are like sort of a niche implementation of generic neural networks, and the typical use case is about image recognition. And that's where they shine. Convolutional neural networks are alone responsible for the explosion of attention that neural networks in general received. Image recognition can be anything: faces, animals, street signs, paintings, just anything. And so if you take a product like a Tesla car with a self-driving pilot, probably the Tesla car is full to the brink of different neural networks, convolutional neural networks. One of them will be trained to see, I don't know, the lights at the traffic lights. Another one will be about velocity, signs. I don't know, but it's for sure full of neural networks, of convolutional neural networks. Another type of deep network is recurrent neural networks, and those are networks that work with processes in the real world where inputs form sequences in time. So where basically the input at any given time is dependent on the inputs that came before it and probably influences the inputs that come after it. And so speech is one of them. You know, words in a sentence, they often depend on what came before, and they have a different meaning or a different nuance, and they, of course, influence words that come after them. And these kinds of neural networks that have this sort of chronological dimension to them are really, really, really complicated. And I think the most common use case that we all have in our living rooms is like Alexa from Amazon, or you know, these Google Home assistants, things where speech is very, very important. There's more types of deep networks, but in this talk we are going to focus on the convolutional neural networks. What are these beasts and what's their power? Well, can I ask you please to just look at this image for 1 second? Well, I am sure that all of you, or at least most of you, will have no trouble telling which one is the cat and which one is the rabbit. And I'm sure not only you didn't have trouble telling the two, but also your brain knew it immediately. Like you saw this picture and you knew. You didn't have to think about it. So if you try to break down that process that your brain went through, it must have been something like, oh, okay, both animals have 2 ears and 2 eyes, 4 legs, and they are both black and white, but you know, the rabbit's ears are longer, or a cat has a longer tail, and you were able to tell immediately the rabbit from the cat. But what if you try and teach a computer to do this? How would you go about this? If you think and try and write an algorithm that tells a rabbit from a cat, it would be incredibly difficult. And this is where convolutional neural networks have their power. The way they work is by, if you take a network, you know, built with all those neurons, and you have, let's say, a lot of images of rabbits, different images, so rabbits of all colors, all sizes, all kinds, in all kinds of situations. Well, and we're talking about thousands of images that are labeled. What you can do is train the network through these images. And what is the network going to do? The network is going to scan through all these images one by one, and with a sort of grid that you see in the lower left corner of this slide. If you imagine that sort of grid, but then at a pixel level, the network is going to scan all these pixels, and each pixel comes with different colors, and it's going to identify some filters that, if you look at the image through those filters, these filters are able to detect whether there is a rabbit in the picture or not. So, in a sense, these filters allow the network to identify the rabbitness of this rabbit. What makes it unique? If you train a network with images of a donkey, yes, there will be similar things because they both have long ears, but the filters will be slightly different, and the set of filters that identifies rabbits will be different than the set of filters that identifies a donkey. So now you know, when you hear the word training a model, train a network, that means identify the best filters for the job. This is, on a very high level description, the way that convolutional neural networks work. And a typical convolutional neural network architecture called LeNet, it was one of the most successful ones, works like this. If you read it from left to right, you can see it maps very well the layers that we saw before. So we're going to have an input layer that receives our images, and then there is this convolutional layer. This convolutional layer is the layer that does the job of applying the filters to the image. And then there's a subsampling layer, which basically just reduces the bandwidth of the information coming from the convolutional layer, followed by one or more dense layer, because so-called it's like 500 fully connected neurons. And then there's an output layer. And at the end of the output of the output layer will be something like there is a rabbit here or not. And in our case, it will be there is a plane or not. Okay, now we establish this high-level view. Let's see how we can build it. Thankfully, we don't need to build all of this up by ourselves because there are libraries out there that have done this for us, and we can just use them. Probably the most famous library is TensorFlow. It's a library that was used and developed by Google. I tried it, but I didn't like very much their APIs. You can clearly see it's built for Python, and there's Java bindings, but I don't know. I didn't feel very comfortable with it. But Deep Learning for J instead is a library built especially, specifically for the JVM, and so it's much more Java-esque than TensorFlow. But feel free, try whatever feels best for you. I really loved working with Deep Learning for J. All right, so how are we going to do about this? How are we going to go about this? First of all, my Raspberry Pi is happily taking images. These images are very big, and they contain a lot of noise, a lot of more information than what I'm interested in. So in order to train my network, I am going to crop the image. I'm only interested in the bridge, and also reduce its bandwidth, because you don't need, if you think about it, you don't need an extremely high resolution to see there's a plane. If you look at the picture on the right, you see that there's a plane. The resolution is really low, but the features of the plane are kept. So you see its color, and you see the sort of the tail. And so what we're going to do is going to crop and reduce all the pictures that come from the Raspberry Pi. This way they take less space and they're faster to read, but crucially it speeds up training. Training a network is not an easy task. My Raspberry Pi, in fact, wasn't able to do the training, wasn't powerful enough, so I ended up doing the training on my MacBook Pro, and then using the Raspberry Pi to sort of use the already trained model. Now, once you have all these pictures, they're all cropped, what you need to do is split this data set into two classes. One class, plane, full of pictures with planes on the bridge, and the other class with no plane on the bridge. And what you need to do here is to, well, basically, you human, you need to look at all of these pictures one by one and label it, whether there's a plane or not. And I tell you, this is not, it's not always fun. It's a very tedious and very long task, also because we're talking about thousands and thousands of pictures. I think I trained maybe 16,000 of them. And once you have done all this work of labeling all of them, you need to divide the whole data set in two subsets. One is going to be the training set that you use to train your network. So it will contain both plane and no plane pictures. And then one set, maybe smaller, usually 80 and 20, will be the test set. You are going to use this test set to check how the network behaves when it's asked to analyze pictures that it has not seen before. And then what you're going to do before giving the training set to the network is you're going to finally write some code. What we need to do is first pass some settings to our Deep Learning for J library, such as the input height or width of the image. In this case, it was 25 pixels by 171 pixel. It's a very random number, and there wasn't really a reason for it. It can be any number, but it's a very small picture. The depth was in this case the number of input channels. So each pixel has 3 colors: red, green, and blue. And then other settings like the number of possible outcomes. In our case is 2, plain or no plain. And once we have all these settings ready, we can go on and build our network layer by layer. Now, this slide will be in Scala, but Java would look practically the same. And what you are going to see is I am going to show for each layer that you see on the bottom right corner, I am going to show some code, how to implement it. And on the left side, you keep seeing the code that I've already shown so that you see all the layers together. It's a bit dense, but I'm sure you can follow. There we go. We start with a classic builder. So new neural net configuration. This is classic Java. Then the first layer, an input type, we're going to have this set input type method, and we're going to specify that the input type is convolutional, and with the settings that we decided earlier. That's our first layer. Then let's add our convolutional layer. So we're going to have a new convolutional layer dot builder. And what are those two numbers? 5 by 5. And also later there is a stride with 1 and 1. What is all that? Well, see this picture? Remember the rabbit with the grid? Those two numbers, 5 and 5, are in fact the size of the grid. So in this case, we are telling the network to scan the image with this grid, which is 5 by 5 pixel. And of course, the proportions you see on the image are, those are way more than 5 pixels, but that's the idea. So the stride, it means how fast is this filter going to move across the image. So we are going to have this square, 5 by 5 pixel, that moves by 1 and 1 pixels through the image. There's going to be 20 output, 20. So remember, each layer needs to have connections to the layer after. And in this case, there's going to be 20 of those like little arcs, little connections between neurons. There we go. Next layer, subsampling layer. It's basically going to reduce half to, you see all those twos, that means half. Basically, we're halving down the bandwidth coming from the previous convolutional layer, so to make computation a little faster. Hidden layer, which in my case, 500 neurons, fully connected, that are going to do all their transfer functions with the input. And finally, we add a output layer, which, as you see, n out with num classes. Remember, that was 2. That number was 2, plain or no plain. And finally, build the entire thing. On the left, you should see the full network configuration. And so a word of caution, if you were to copy-paste the code from these slides, it wouldn't compile. This is a bit of a simplified version, but that's the idea. If you want to build your own network, this is what you would do. Yeah, again, there's more settings and a little more things here and there, but this is the basic idea. All right, now we have our network. How are we going to train it? This talk was meant to be, live with a Raspberry Pi on stage and all of that, but because we are in this remote world now, all we see is a screenshot, and I reckon it's not as fancy as a real Raspberry Pi. But so what you see on screen is the log of a training run. Basically, for each iteration, the Raspberry Pi, the training of the network is going to look at all the images of your training set and then test the model on the test set. What is the outcome of a training run? Well, you know, a training run means identifying these filters and identifying, well, in practice, identifying these filters means tweaking the weights on the inputs of the transfer function of each single neuron in your network. So each iteration, which in deep learning terminology is called epoch, at the end of each iteration, those weights on the transfer function inputs of each neuron will be different than another iteration. It's kind of random. It goes through each images, probably in a random order, actually not probably, in a random order, and tweaks the weights on those inputs until the results are satisfactory. This basically for you is the like end-to-end training of the thing. And then at the end of each epoch, it will estimate using the test set a score where 1 is the best possible value. That means the network never gets it wrong. And then if you look at the last few lines, you see that the best score was at epoch number 5, I believe. Yes, so that's 0.96. We'll see later what the score means, actually. All right, so we have run this training, and now we have a model that is fully ready to be used in real life. How are we going to check the performance of our network? Do we need to, I mean, it's reliable enough? It's not reliable. The performance of your model can really make or break your case. If you have a deep learning network to identify images for a very sensible purpose, such as in a medical industry, you have some MRI scan and some sort of scan, and you want to identify if a person has cancer or some other disease, then you want that your model to be very reliable. How do we measure these results? We use the so-called confusion matrix. So the idea is, every time that you give an image to your network and the image does some recognition on it, it falls in one of these 4 cases. So top, left, true positive. In our case, in our plane case, means that there was a plane in the picture and the model saw it correctly. So true positive. Conversely, at the bottom left, false positive. That means that the model saw a plane, but there wasn't any. And if we go to the right section, a false negative at the top means that there was a plane, but the model didn't see it. So the models tell you there's no plane, but there was actually one. And bottom left, a true negative prediction is when there was no plane and the model didn't see one. So these 4 cases. Now, when you map these 4 cases to the actual outcomes of your network, then you can have access to a set of different measures. In this case, we're looking at 2, precision and recall. The precision is a measure that tells how well the model avoids false positives, whereas the recall tells you how well the model avoids false negatives. And the way to measure this is actually, again, for each prediction that your Raspberry Pi, your trained network does, you as a human, you need to go and check whether the network was right or not. So again, this is not an easy task, and it's a lot of work. That graph that you see on the right, there's 2 lines. The precision line is the blue line, and actually you can see that it's pretty high. Over time, it's almost always consistently good. Some days it's even 1, which is the top result. That means that every time that there was a plane, the network saw it. Or better, if the network says that there is a plane, the network is probably right. The recall, though, the red line, you see it's very oscillating and it never goes very high in score. That means that the network missed quite a few planes. So when the network says, okay, there is a plane in this picture, there probably is, but there's many pictures where there is a plane and the network doesn't see it. And well, in my case, in our case, why does it go wrong?
If you want to do that stuff.
Oh, was there a question? Oh, well, so why does this model get it wrong sometimes? Well, in my case, it's because of the weather. So as you can see, for instance, in the top left picture, there's a very thick fog, so it's probably difficult for the network to see the plane. In the bottom left, there is actually a plane. If you squint, you'll see it, but the sun is just in front of the camera, so the resolution, like the contrast, is very high and everything is very dark. In another picture, it's raining, so of course there's drops on the window, and that confuses the network as well. And probably the most fascinating is the bottom left image. Sorry, bottom right image. Of course, for us humans, it's so easy to tell that there is a plane on the bridge, but the network only sees part of the plane, and maybe its filters have been trained, that if it doesn't see the head, that is a big piece of information missing for it. This really should make us, conscious that our brain is so incredibly powerful. And also there's another thing that I want to focus on as one of the last slides, why the network got some bad results sometimes. Well, it's AI bias. Even for a playful, sort of useless, if you want, network like this, I encountered AI bias, and I didn't think about it beforehand. In the Netherlands, where I live, the national air company is called KLM, and its planes are blue. And so that means that during the training phase, my network has seen a lot more blue planes than planes of any other color. So what happens is that when there is a blue plane on the bridge, the network is like, oh yeah, sure thing, of course I see a plane. But then when there's a white plane or a red plane, the network has troubles or has a lot less, the network is more confused. It's less sure about its own predictions, because if you train a network with planes in the Netherlands, the network's going to think that all planes are blue. And AI bias, it's, I think is one of the greatest challenges of humanities going forward. Of course, there's climate change and many other challenges, but AI bias is one. Prejudice in artificial intelligence is extremely difficult to avoid. So if you are a bit curious and interested in these topics, AI bias really is a very big challenge. So that's basically it for me. What are the next steps for you if you found this talk inspiring? Well, first of all, there is a blog post that goes with this talk that goes over the same concept, focusing a little more on the rabbits and the cats. And then you can read about deep learning and convolutional neural networks. For my own project, I used that book there called Deep Learning, a Partitionless Approach. It uses deep learning for J, so all the examples are tailored for the JVM, Java or Scala. The book itself is not very recent. It's from 2017, but the core concepts haven't changed. And then I would say find a fun use case and a data set and start experimenting. If you want, you can use my planes data set. Is available online. But it's even more fun if you find a use case that it's a domain that you already know. If you have some passion for fishing, you could do something with fish recognition, or maybe something at your job, at your work. I think having fun with it is the most important thing. And this concludes my presentation. So thank you all very much for your attention.
Thank you.
Thank you, Fabio. Thank you so much. Does anybody have any questions for Fabio?
I just had a quick one. This is Arvind here. While working on the deep neural networks, one of the things that I sometimes get a little confused is like when you export so many images, so technically it's forming a matrix basically, right, of your neural network. So does JVM ever go out of memory or something of that sort? Because it's in a virtual environment, right? And you're kind of training it in the virtual environment. So ever think of that situation ever occurring? And
yes, all the time. This is one of the main reasons why you want to keep your images very, very tiny as possible. For instance, if you can make them grayscale. I kept the colors, but looking after it, if you saw my AI bias issue, then maybe I should have removed the color. And my Raspberry Pi couldn't handle the training, even with those. It was maybe about 16,000 images, and all of them were tiny with a little low resolution, and still it wasn't able to cope. The Raspberry Pi has 4 gig, and it ran out of memory. Exactly. So yeah, this is why we only AI and convolutional neural networks only started exploding in the last decade or so, because before simply that amount of power wasn't easily available. So yes, absolutely.
And this is running on a JVM, but yet makes use of the GPU also, right? I'm just trying to understand this.
Yes, a GPU is if you have a GPU, it's really useful. Maybe goes faster or whatever, but you don't need one. But if you do, it's certainly beneficial for the training phase.
Yeah, because I did hear you using a MacBook Pro, so I was thinking, did you use an external GPU or an eGPU to work on this model? So
yeah, that sounds also a fun thing to set up. Yeah.
Thank you.
Sure, thank you. Anybody? What's your domain that you could find something interesting to do?
Yeah.
How about baseball? I think baseball is an important sport in the US. How about
ball?
Yeah.
Sorry, besides, you mentioned at the end, potentially going to grayscale. Are there other thoughts you had about kind of overcoming the bias you found in the results you got? So,
thanks for bringing this up. I really care about AI bias, and one of the common misconceptions is there are a lot of TED Talks, for instance, or articles out there that blame engineers for AI bias. Like, oh, your algorithms are full with your prejudice. In reality, it's not the algorithms, but it's the training set. And so what I advocate for is that we engineers need, the developer that actually connects all the pieces of the puzzle. I shouldn't be the one choosing a data set. I think choosing a data set so that it's heterogeneous, so that it's well balanced. That there's all sorts of racial issues coming out, skin color, gender. It should be choosing the data set that is very well representative and inclusive is a task that should be given to someone who is whose profession is that to a sociologist or not to an engineer. And so I don't know, but I really feel this topic, and I think there is so much. There is really a bad misconception about how deep networks work. It's different than an algorithm. It's all about the data set, and choosing again a heterogeneous and balanced data set. It's very, very complicated, and I think that would be in my case. If I had made the planes gray, I actually tried that, but the network wasn't very able to distinguish them, or better, it was more difficult because when everything is gray, then the planes blended in with like the clouds behind them, or it made it less obvious. But thanks for the question. Yeah, thanks.
So I think for me, I'm kind of new, if you don't mind. So for data set, you're saying that we should actually involve essentially like subject matter expert, right? Sociologists, like you said, somebody to get involved with creating data sets. But in reality, who are the ones creating these data sets right now? Do we know, or are they, when they get published, are they really, what people are publishing them? Do we know? Do we even know?
Yeah, thanks, Mary, for this point. I think you're totally right. It's a matter of transparency. Yeah. One of the most famous data sets used in it's a bit of a academic, if you want, like a toy data set is a data set released by Zalando. It is a very big clothing company. They released a data set of about 60,000 images of clothing, and so the idea is that there is one image has a shoes, another image has a t-shirt, or another one has a coat, and then you can use that and train your network to tell you which piece of clothing you're looking at. Well, nobody knows who created that data set. It's just out there, and if you take sort of blindly that data set, there is no guarantees that come with it that is balanced. Maybe there are more shoes than coats, and there is no accountability because the company did that, but within the company, I mean, nobody knows. Maybe they were just chosen by a developer, or it could be the CEO. I don't know, but the point is we don't know. For instance, what is IBM's policy with this? There is this cloud AI called Watson, where you can submit your data set, and I guess do you need to specify your sort of, if it's a public data set, are you required to sort of explain how it was assembled? I don't know.
Yeah, you're right. I think that's a very new area. I'm not like very much involved with that, but that's very valid and very good question too. Like you said, a lot of times we just get data, we assume it is just there, so we use it without even thinking, well, who created that? How did they get assembled? Are they representing a balanced set of data or something? Nobody, like you said, maybe nobody actually even asked about that. But as far as IBM goes, now that you have brought it up, that's a good question. Let me also go back and ask, like the expert, the subject matter expert in this area. That's very good. Now let me ask them, and I'll get back to you about that too. Once I hear about something, on this.
Oh yeah, that would be really interesting to know. Yeah.
Exactly. Very interesting. Yeah.
I have a question for you. In a lot of the examples I've seen of neural nets, like for example, the image processing thing, you're sort of always dealing with a fixed size of data set, right? You have specific pixel dimensions you'd be using. And I don't know if this is the right question to even ask, But what if you had, say, data that was maybe not an image, like records of some sort about something, and those records would have like fields that you want to do learning on? From what I've seen, it seems like you might want to break those fields down into like the unique, distinct values they could be, and maybe numerically represent those. But one question I have is, do you have any recommendations on how you would take, like, let's say the number of fields could be dynamic, right? It could change on a given record, for example. Is there a good way to represent that with a neural net, or would a neural net just maybe not be the right thing for this?
Well, thanks for asking this question, first of all. Neural networks are, by definition, a bit more complicated and computationally intensive than other machine learning tools. And neural networks are really only required when you are dealing with unstructured data. So an image or a waveform from some audio, we would call that an unstructured data. For structured data, like coming from a CSV or an Excel file, which I believe you are maybe referring to, there are other ways to do prediction on it. There's and so a lot of libraries like Spark, they come from with their own machine learning subset, which is not deep networks, and those tools are optimized for the cases that you're talking about. They are a bit reactive in the sense that they are resilient if one field is, one row is missing one column or things like that. That there's a way around it. And if you're interested, give a look to these other machine learning ways that are not deep networks, because these other machine learning ways are, I don't know much about how they are implemented, but what I know for sure is that they are way less computationally intensive, and in terms of resources, they're probably even my Raspberry Pi could run them.
Okay, thanks.
Sure.
Anyone else have questions? More questions for? No. It doesn't look like maybe it's a Saturday and folks are relaxing. So yeah, it's a very beautiful day here too in Chicago. So yeah.
Also, I guess, like I said, there was not a lot of code in the presentation at all. It was more about concepts, and so maybe with more code there would be more. Oh, how do I do this? But
yeah. But that is still good. I mean, it's a new area of and also
yeah. Oh, sorry.
Oh, and I was going to say, it's nice too, you are sharing a project you're working on, and kind of as a side project. I think that's always good. And on the weekends to talk about these things are really good. So it's like, giving me idea to see what I can work on too. So that's very inspiring. So thank you.
Yeah. And I'm sorry, folks, if I maybe stressed that a little too much, but I really care about AI bias. When I realized this blue planes issue, it hit me like a wall. And what if my project instead was, a lot more sensible than just seeing planes on a bridge?
Yeah.
It was just an incredible feeling of wow, yeah.
You're right. Yes. Yeah. That's correct. Yeah.
I think what you see on Facebook, and it just makes you more and more biased, almost, the algorithms that they use to post ads to you.
Yeah.
It just caters to the things that you've already looked at and doesn't let you experience anything new, sort of.
Absolutely.
Sort of thinking about that too.
Yeah.
Absolutely. The most famous example of a very, very sensible topic is if you if you use LinkedIn as a base to sort of look at the composition and job roles and all of that, then you would guess the best, the best people to be CEOs of successful companies are white male. Simply because that's how reality unfortunately is. And it's not the fault of the network, and it's not the fault of the developer who actually built the layers. It's just a very skewed reality. And so if you train a network with these skewed sets, the network cannot do anything else than replicate the prejudice and the current status quo. And again, I see all these talks and articles that are against neural networks because they're biased. Technology is not guilty of anything. It's just that it can only reflect what it learns from.
Yeah. Sure.
Yeah. So yes, I think Stacy, I think Facebook and Twitter and social media in general, of course, are a prime example of this. Yeah. So thanks for your observation.
Thank you.
I guess along those lines, are you aware of any like groups in either in technology or maybe even not, but that are like specifically focused on that area with the AI bias, or maybe working to come up with either recommendations or guidelines for people looking to use neural networks?
Okay.
Yeah. Me personally, not so much. I'm not part of a specific work group on this, but what I try and do is every time that I read something that is a bit incorrect, at least from a technical perspective, I try and point it out. Maybe to very respectfully tweet to the journalist that wrote that specific article and try and make the difference between algorithms and deep networks more clear. But actually, does anybody in the audience have some idea about this? Is there some work group or something?
Sure. So for me, remember too, there's actually not so much of a group or more like a what you call like a consortium to address this issue, but I know there's this thing called AI Fairness 360. It's like an open source toolkit that, for example, IBM, and I just posted a link to it. But at least I'm aware then that's something IBM has, as expressed in the form of source code to address this. As an open source kit for developing more fair kind of development. Yeah, for an AI fairness toolkit. Yeah, from the IBM research. So that I'm aware of one thing, but I also believe that because the IBM is very much involved with AI, machine learning, all these like data analysis, data science. So I'm sure too there are many things going on, and I've heard about it. It's just that I have not been too heavily involved with that. But now that you mention about it, maybe if I should ask more and then give you some more information on that, and also like to see what it is in the industry, what the industry is doing to address this kind of a very important issue, actually. It's kind of becoming more social to this thing. So
yeah, thanks, Mary. This looks beautiful.
So maybe that's something it's good to.
Yeah, I really like this. I clicked the link you sent, and I almost feel like every company, I'd done some AI stuff in the past at previous jobs, and your comments about how data sets are picked, I completely agree with. I think, sort of at some of the companies I've worked at in the past, it was just up to the engineers to sort of compile data sets together. And I had the question too, then I was like, I honestly don't know what I'm doing with this data. Like, I understand the structure and the format, right? I can feed it into a model, but I feel like you're sort of giving me this power that I don't feel I should have. And so I like the idea you mentioned, like having a sociologist, somebody who specializes in that particular area of expertise is great. And I think just in general for myself moving forward through my career, anytime there is some kind of an initiative that comes up, I think it might be a good idea for me to just like say, hey, we really should just form a team of people who specialize in this area so they can catch these things. Because you're right, like me as an engineer, I'm sort of focused. My headspace is getting the thing to work. If you're releasing this as a new feature or something, it's like, yeah, we're excited, let's get this to work. But then you don't always step back and think through those bias issues. And then your software starts doing things, and you're right, like engineers get blamed, and it's like, that wasn't my intention, but you're sort of stuck with this monster you've created. So I really like that idea, and I appreciate you calling that out and saying that. It's just something I think for me to be more aware of moving forward. Anytime data sets come in like that, yeah, let's get people who actually understand this involved and not leave it up to me. So,
yeah, very good point. Yeah, wonderful.
Yeah. Thanks for your point, Matt.
Thank you. So,
Can I ask about linear regression? You use it for classification, I guess, in your project. Do you use ever a logistic regression in some project? Or does logistic regression can be used for this kind of networks?
So our plain use case was about classification, and I don't know much about regression cases, to be honest, and especially not with neural networks. So, but maybe someone else in this audience knows better for your question.
Okay, I guess not. Thank you.
Okay, so does anyone have more questions? And I guess we can always reach you too, Fabio. We'll follow you on Twitter and ask you questions there too.
I should actually join your Slack community.
Please do. Yeah.
Yeah. It from your introduction, it sounded really wonderful.
Yes, let me do that. Just talking about it, but without sending out a link to join. And let me kind of make sure I give the right link. So give me a minute. There should be a link somewhere.
During your introduction, I was listening to all the wonderful things that you have organized with the Chicago Java user group, and I was like, oh man, I'm such a bad organizer. Like, I don't do a tenth of all these wonderful things.
It's just so happy we have many things. Yeah, it's kind of all we inherited, right, from folks starting to do it, and then just kind of building upon it. So yeah, but thank you. So yeah, let me yeah, this is the link I just posted to join the Chicago Tech Slack. The only thing is it's a community Slack, so it doesn't save like archive too much. It is a free tier, so. But I'm actually thinking of we should actually start something on Discord too. I don't know if anybody used Discord, and something that I just recently get more involved, because actually I have a Twitch stream too, and Twitch, I think the gamers are using this Discord server, and that one they actually have unlimited like message size for your channel. So
also for tier.
Yeah, but for Slack it's good too. It's just that for tier, then our messages will go away. Like it doesn't get archived beyond, I don't know how many, like a size, right? Certain size, and then they won't archive that beyond that size. So maybe I'll look into getting a Discord set up too. Oh, let me see. I think Arvin, a comment? Yeah.
Oh yeah, just a thought. Like, would it be cool to just create kind of a Maven archetype for such deep learning projects? Like, usually, although I know that all the jars and everything are available, but it would be kind of cool to have some kind of a Maven archetype that sets up this entire project for this. Like put your data sets here, define your classes here, and this is how you export your model, and it can become kind of a reusable template. Just a thought, or maybe it's already there. I'm not aware of it.
Yeah, that's a totally good point. There's also, like Mary was saying, from IBM, but also from Google. There's all sorts of libraries, templates, starting points. And me personally, for this little project, my goal was really starting from scratch. And like in the beginning, I submitted my pictures to some Google API, or maybe it was on Azure, I don't remember. And so you send the picture, and then in a millisecond the API tells you, oh yes, there's 3 cars, there's 2 trucks, and 4 trees, and there's no plane, and 10 buildings. But that wasn't fun to do. I really wanted to build it myself. But yes, there's so much material out there. It's just an ocean of things that are available.
Mm-hmm.
Yeah,
that's right.
Cool, thanks.
I just joined the community, actually.
Oh, okay, great. Yeah. Right now, I think there are 10,000 people. Wow, I just noticed. Yeah. So wow. Yeah, it started maybe 3 years ago. Yeah. So we have many channels now. So.
Yeah, it's incredible. 9,000 people. So basically, the Slack community edition is limited in history, but there is no limit on the amount of members. Is that correct?
That's correct. Yeah, members are no limit, but the message. I should take a look too. That one is the standard. Yeah, so we're on the free tier. It doesn't say. I thought I saw it before, maybe like 10K messages or something. That's all it saves, and so yeah, it just cannot be saved. So, but
wow.
Okay, I should.
Really cool.
If folks want to join.
Thanks for inviting us.
Yeah, you're welcome. Yeah, so stay in touch that way as well. So yeah, so it's almost like 30 minutes past the hour. So yeah, I have to be cognizant of the time zone. So does anyone still have any more questions at this point? If not, then we should end this meetup. But I actually am still going to be leaving this open for anyone who wants to talk and chat and just casually doing, mingling too. So until the last one leaves, so I'll leave this on for now. So you're welcome to hang on. Bring a drink from your refrigerator. Too bad we can't have like drinks, kind of like at a place where we can order drinks, where we can go to your refrigerator, get something to drink. So yeah, and then we can hang out here for a bit too, as long as you wish. So yeah. So with this, I'd like to say we are ending today's meetup, and thank you again so much, Fabio. Thank you so much again for the case group and Andy and Mark being here. Thank you. I think it's been very nice, the conversation and bringing up AI fairness, and it's just a really larger issue that the world is facing. So thank you so much. And yeah, we should have you back again, and we should continue the conversations too. So yeah, thank you very much. Yeah. Okay.
Yeah. Thanks everybody for having me and accommodating again the time zone. I think I'm gonna have dinner. It's pitch black outside, and I haven't yet. So
dinner. That's right. Yes, that's right. In Italy, or your practice, you eat dinner late, right? In Italy, is that correct? And in general,
yes,
right?
Yes, true. But in the Netherlands, I got used to have dinner at 6. And so I'm very behind schedule tonight.
Okay, you're going back to your Italian way of eating late. So yeah. Okay.
Thanks everybody for having me and for your attention and questions. You really are wonderful, and it's a wonderful communities.
Thank you.
So-
Thank you.
Thanks, Fabio. Appreciate the conversation.
Yeah,
Yeah, thank you.
Yeah, thank you so much. That was really great.
Thank you.
Okay. Have a good night, Fabio, and good night to
You.
Helena. And yeah, and then the rest of you in Chicago enjoy the day. It's a beautiful day outside. So thank you. Bye bye.
Bye.
Bye.